Hello, welcome to my video on data structures. This is part 2 for the queue and stack data structures. In this video, we will talk about the implementations of queue and stack. Recall that queue and stack are derived from array or linked list. Therefore, we can implement them based on array or linked list. Let's first look at the pros and cons of both implementations. If we choose to implement queue and stack using linked list, the main advantage is its simplicity. That is, there is essentially no re-implementation needed, and we just need to rename a few operations. Meanwhile, because linked lists allow constant time insertion and deletion at any location, all of the stack and queue operations can run in constant time. The disadvantage of the linked list implementation is that it consumes more memory, which is primarily used for storing the prev and next links in each node. Data access with linked list is also slower. This is because we only keep track of the head and the tail nodes, which are both sentinels that do not contain any real data. In this case, to access the first or the last data element, we will need to follow the next or the prev pointer of the head and the tail node. It thus makes the data access comparably slower than data access in array using index. For the array implementation, it does not need to store the prev or the next pointers, and it is thus more memory efficient. It also offers faster data access as we can directly access data elements using their indexes. However, we may encounter the data overflow issue when inserting new data elements to array. In this case, we will need to perform time-consuming memory reallocation and data move to increase the capacity of the array. Therefore, the push operations for stack and the enqueue operation for queue may take linear time in the worst-case scenario. Another issue for the array implementation is that we will need to make substantial changes for the queue data structure for a reason that will be clear later. Here we summarize the function name mapping on the left panel and the time complexity for the operations on the right panel. Recall that stack and queue only access, insert, or delete the first or the last data element in the list. In this case, we can leverage the head node and the tail node of the linked list to quickly locate the data element we need to operate on. Meanwhile, inserting or deleting elements from a linked list only involves a constant number of pointer changes. Taken together, all stack and queue operations can be done in constant time. Specifically, we can simply rename the corresponding functions using the name mapping when implementing the stack and queue. For example, we know the push operation for stack and the enqueue operation for queue both correspond to the pushback operation in linked list. In this case, we will simply copy the function body of pushback and rename the function to push or enqueue under different data structure context. Note that we may consider declaring the insert function as private for stack and queue. This is because we want to prevent the user from accessing or modifying data at any location of the list to ensure the first in, first out, or the last in, first out behavior. Okay, now let's discuss the array implementation. Unlike the linked list implementation, we can see that some operations here cannot be done in constant time. For the push operation for stack and the enqueue operation for queue, they both correspond to data insertion operations and may trigger data overflow of the array. In this case, we will need to move the existing data to a new place with a higher capacity. This worst-case scenario requires linear time O(n), where n is the current size of the array. A more challenging case is the dequeue operation that deletes the first data element from the array. In this case, we will need to move up all subsequent data elements by one position to eliminate the hole created by the deletion. That is, we will move the second data to the first position, the third data to the second position, and eventually the nth data to the n-1th position. The dequeue operation thus requires linear time O(n), which is consistent with the linear time complexity of the deletion operation in array. Note that such a linear time complexity is substantially slower than the constant time complexity for the linked list implementation, and is intolerable if the dequeue operation is frequent. As a result, we would like to modify the array implementation and make the dequeue operation run in constant time. The solution is to implement a circular array with floating front and end. Specifically, Front and end are two array indexes that point to the first and the last data elements, respectively. In other words, they characterize the range of the data elements. When we dequeue to delete the first data element, we can simply increase the front index. Note that we may leave some empty memory blocks at the beginning of the array in this step. When we enqueue to the end, we can simply increase the end index and then write the data. If the end index reaches the last position of the array, instead of directly increasing the capacity, we will reset the end index to the beginning of the array. In this case, we can make use of the empty memory blocks created by the dequeue operations. As a result, unless the size of the queue exceeds the capacity, we do not need to perform the resize operation. Let's use a toy example to illustrate the idea of circular array. Starting with an empty array, we set the front index to an arbitrary index within the range, and the end index one position before the front index. We also set the size of the array to 0. The first operation is to enqueue 18, and we first increase the end index by one position and write 18 to the position pointed by the end index. Note that we also need to increase the size. The second operation is to enqueue 2, and we do the same thing as before, increase the end index, write the data, and increase the size. Let's continue with the third enqueue. We observe that the end index has reached the last position of the array. However, the size of the array, or 2, is far from reaching the capacity of the array, which is 5. In this case, we know the queue can hold another number. Therefore, we reset the end index to 0, write the data 27, and increase the size to 3. The fourth operation is a dequeue operation, and we can simply increase the front index. The last operation is also a dequeue operation. However, as the front index has reached the end, we will also reset it to 0. Note that at this point, both of the front and the end indexes point to the same position, indicating that the data element stored in the position is both the first and the last data element. In other words, the data element is the only one stored in the queue. Given the above intuition, let's sort out some implementation details. First, we can initialize a circular array with 3 steps shown here. They are assigning the front index to an arbitrary position, assigning the end index to one position before the front index, and setting the size of the queue to 0. In a special case, where the front index is set to 0, the end index will be set to the last position of the array. Now, let's see how the major queue operations can be implemented with the circular array. For top, we will first ensure that the queue is not empty, and then directly return the data with the front index. For enqueue, we will first increase the end index. Note that we will use the modulo operation to reset the end index to 0 when it reaches the last position of the array. After increasing the end index, we then write the data and increase the size of the queue. Finally, for dequeue, we will first make sure the queue is not empty. Then, we increase the front index and decrease the size of the queue. Note that we also use the modulo operation here to reset the front index when it reaches the end of the array. Last, we'll discuss two miscellaneous issues. The first one is the handling of data overflow. Its detection condition for the circular array is the same as that for a regular array. That is, when the current size plus the newly inserted data exceeds the capacity of the array. Overall, the handling of the overflow also follows that for the regular array. That is, we first resize the array and then copy the data. The only thing we need to pay attention is that the data elements in the old array may not be linear. In this case, we will need to modify the data copy code accordingly to account for the circular data storage. Second, I would like to note that the index configuration for an empty queue is identical to that of a completely full queue. Specifically, the end index is one position before the front index in both cases. The only information we can use to distinguish these two cases is the size of the array. As a result, keeping track of the size is important for the correct implementation of the circular array. In summary, we have discussed the implementation of stack and queue in this video. We know that both data structures can be implemented based on linked list or array. Linked list-based implementation is simple, and we do not need to make significant modification to the original code except renaming several functions. For array-based implementation, we do not need to make significant changes for stack either. However, we will need to re-implement the circular array for the queue data structure to ensure the constant time dequeue operation. In the next video, we will show the actual implementation of stack and queue using array. We will skip the linked list-based implementation as it's trivial. Thanks for watching and hope to see you next time.